Any power conversion module has an efficiency which is lower than 100%. That means that the input power will be almost transferred to the output side, but part of it will be dissipated in form of heat, and that will cause a temperature increase of the module. The two formulas below the drawing shows the relationship between input power and output power through the efficiency parameters, which is indicated by the Greek letter eta. The heat generated inside the module will be dissipated or removed through the metal base plate, which is part of the module case or packaging. The base plate is thermally coupled to the internal power dissipating components, to the power devices, but it is electrically isolated from these for safety reasons. There are basically three methods of power dissipation. One is the conduction cooling, one is a convection cooling method, and the third one is a radiation method. This three-dimensional diagram shows a typical efficiency performance of a specific Vicor part. The efficiency is dependent from the input voltage as well as the output load. It is possible to notice that on a very wide operating range, the efficiency is almost flat and constant and set to a fairly high value, above 85%. By means of these diagrams, it is possible to determine exactly what the efficiency will be once the operating point is known in terms of voltage, input voltage, and output current. And by knowing the efficiency with the formulas presented before, it will be possible to calculate the thermal dissipation and the temperature increase of the module. Once the thermal parameters of the design has been calculated, that means the thermal increase, the temperature increase, the power dissipation, and once the surrounding conditions are known in terms of, for example, airflow and ambient temperature, it is possible to choose the proper heatsink either from the assortment that Vicor offers in terms of accessories or from third-party manufacturers which offer broad range of different shapes and size of heatsinks that could accommodate any kind of application. With this experiment, we will now analyze the thermal characteristics and the thermal performances of a modular power supply. The setup is fairly simple. We have our experiment box, which holds one module, supplied by the input source and loaded by an electronic load here. On the module, we have applied a temperature sensor that allows us to read the temperature on the base plate of the module itself. Any module has an efficiency which is lower than 100%, so that means that part of the input power will be dissipated by the module itself, and this will be converted into heat and therefore will cause a temperature increase. With this box, we can easily read the input voltage and input current as well as the output voltage and the output current. And this is very important because we can exactly calculate what the input power is and what the output power is, and the difference between the two, which is the power dissipated. Our ambient temperature is now 33 degrees C, therefore we can keep that as a starting point and see what the temperature increase will be. We'll switch on the module now, and we can set up the input voltage to exactly 24 volt. It's very important to make a precise reading of the displays in order to have an accurate calculation of the efficiency. The input current is 2.36 amp because we have set an output current on our load of 2.06 amp, and the output voltage of the module, it is a 24 volt output, and we read exactly 24 volt. So in this way we can easily calculate the input power and the output power and get our power difference, which is the power dissipated by the module. So at this point we can leave the system as it is and wait for a while until the conditions stabilize and the temperature increase will reach its final value. Then we can read the final temperature, and then we can calculate the thermal characteristics of the system. Now that we have collected all the experimental data, we can complete our calculations and verify the thermal characteristics of our system. The input power to the system can be calculated by multiplying the input voltage by the input current. So we have 24 volt input multiplied by 2.36 amps gives us 56.64 watt input power. The output power as well can be obtained by multiplying the output voltage by the output current. So we have 24 volt multiplied by 2.06 amps gives us 49.44 watt. The difference between the input power and the output power gives us the power dissipated, which is the power that eventually will be converted into heat. So we have 56.64 minus 49.44 gives us a power dissipation of 7.2 watt. The efficiency of the module is the ratio between the output power and the input power. So we have 49.44 divided by 56.64 gives us an efficiency of 87.29%. The efficiency of this module, as specified in the datasheet, is 87.4%. So that shows a very good consistency between what is specified on the datasheet and what we have calculated by an experimental method. What we can also calculate now is the thermal impedance of our system toward the ambient. The power dissipated is 7.2 watt, and we had a delta temperature increase, which is 80 degrees C, what was reached on the heatsink, minus 34 degrees C, which is the ambient temperature at which we run the experiment, gives us a delta T of 46 Kelvin. So by dividing the 46 Kelvin by the power dissipated, 7.2 watt, gives us a thermal resistance from the module to the ambient of 6.38 Kelvin per watt. The heatsink that we have used is the one that is indicated in this drawing, and for these heatsinks the thermal impedance as specified is 6.34 Kelvin per watt. So again, we show a very good consistency between the specified data and what we can calculate with our experiment. Another interesting data can be taken from this family of curves. This is a tool which is available on the internet site from Vicor. In fact, the heatsink we are using is a Vicor part number. And the first curve here tells us, according to the ambient temperature, which would be the maximum output power that we can take out of the module without any forced ventilation, just by natural convection cooling. So if we take the 35 degrees C ambient point, we see that in this case the specified maximum output power is nearly 50 watt, which is exactly what we had in this configuration, which is 49.44 watt. And with this, we can also see that these curves are a little bit conservative, which is good for a good design, because we saw that by running the module at 50 watt output power, we had an increase of temperature up to 80 degrees C, which gave us a 20 degrees C margin before reaching the 100 degrees C limit. So the design engineer can use these curves for its design and can apply the data from these graphs directly, still maintaining a good margin, and therefore it could be sure that the design will be correct and there will be no danger of exceeding the rated limits of the module.